thank you very much for sticking around until the very last talk of the conference. I'll be talking about non-stochastic Hamiltonians and quantum annealing of Ising spin glass. And this is a work that is mainly evolved into a collaboration with Matthias Troyer, as well as Ethan Brown and Giuseppe Carlo, who provided the bulk of the data. Yeah, you heard about this stochastic versus non-stochastic a lot in this conference, but just let me give you a definition one last time. Stochastic Hamiltonians have a formal definition, and that basically states that in the computational, for these the matrix representation of these Hamiltonians in the computational basis is either diagonal, it has or it has off-diagonal matrix elements that are negative. And the physical systems that correspond to these Hamiltonians are basically all bosonic systems, non-frustrated magnets, and those fermionic systems that do not suffer from the sign problem. Which means, and this not suffering from the sign problem, again, which means if these problems are not hard for other reasons, then quantum Monte Carlo is going to be efficient for them. OK, so numerically, it's been, as we actually heard about it in this conference as well, it's been shown that quantum Monte Carlo and quantum annealing show the same scaling for tunneling problems. And this numerical observation basically leads to this conjecture that if a problem is inefficient for quantum Monte Carlo, then it's probably also inefficient for a quantum annealer, which works with a stochastic Hamiltonian, which basically has a stochastic Hamiltonian. And then this conjecture, if true, then it basically, if we want to pursue quantum annealing, just leaves us with basically seeing how efficient non-stochastic Hamiltonians can be for quantum annealing. And that's basically the question I'm trying to answer, well, not to answer, but to shed some light on in this talk. OK, non-stochastic Hamiltonians basically are those Hamiltonians which do suffer from the sign problem. And this corresponds to Hamiltonians of most fermionic systems and frustrated magnets. And by definition, quantum Monte Carlo is inefficient for them. Non-stochastic Hamiltonians as such are more complex and cannot be efficiently simulated with classical computers. And I should also mention that, again, as we heard about during this conference, and it's sort of a well-known result that if the problem Hamiltonian in adiabatic quantum algorithm can be encoded in terms of non-stochastic Hamiltonians, then universal quantum computing is possible. But now we want to answer it, we sort of want to look at this non-stochasticity in the context of quantum annealing. And the question we try to answer is that can this additional complexity can actually help us solving hard optimization problems in the context of quantum annealing. And by that I mean, if we start with a problem Hamiltonian, which is a stochastic, but it's still hard, if we add additional terms to our Hamiltonian, our annealing Hamiltonian, such that the total Hamiltonian becomes non-stochastic, whether the addition of these additional terms actually help us solve the hard stochastic problem Hamiltonian. So that's the statement of the problem. And I should mention, so this is a numerical work. So we picked a particular problem, in particular a version of Ising spin glass problem, which is similar to the Sherrington-Kirkpatrick model, in which we basically define a problem on a fully connected graph. So every two spins are interacting with each other. And are coupled to each other, and then the couplings are basically randomly chosen from a Gaussian distribution. And in addition, we also add random fields to each spin. Again, the strength of the random field is also chosen from the random distribution, Gaussian distribution. And it's been shown that this problem, obviously, okay, it's infinite dimensional. And it's been shown that its worst cases are NP hard. So it's a reasonable problem to look at. And as for additional terms, as we heard this morning from Peter's talk and also other talks, probably the simplest term that we can add to these Hamiltonians is an XX term with a positive sign. And then the combination of these XX terms and the problem Hamiltonian in the Z basis basically gives us an intrinsic non-stochastic Hamiltonian. And so, but note that this we're defining these XX couplings with positive signs on a fully connected graph. And if we start with if that is our starting point, We know that if we have antiferromagnetic couplings on a fully connected graph, then that leads to a huge, basically frustration and a huge degeneracy. So that's a bad place to start our annealing. So our initial Hamiltonian, initial starting point shouldn't be this Hamiltonian. So for the annealing schedule, I basically picked this annealing schedule from Elizabeth's paper back in 2014. So we start with the traditional starting point of adiabatic quantum algorithm, which is where the ground state where all the spins are lined up in the x direction. And then we linearly decrease the strength of this transverse field, basically, and linearly increase the strength of the problem Hamiltonian. And in the middle, we turn on and off these additional terms. And in the addition of these additional terms basically should make our Hamiltonian non-stochastic. So one choice is, as I said, just adding XX terms with all positive signs, like a uniform XX term. We also looked at a combination of both signs, plus and minus. So in this talk, I'll be showing you a version where we look at random signs, but we also looked at other combinations of plus and minus when it's not random and when there's some patterns in that. But the results are actually very similar, and I'm not going to show the results in this talk. So these two are our non-stochastic Hamiltonians. And then to basically, so note that when we add these XX terms to our Hamiltonian, the sort of, you can think locally that the effect of that is that instead of, whereas when we have an X term, it basically flips one spin at a time. When you add these XX terms, it corresponds to flipping two spins at a time. So in order to try to distinguish the effects of non-stochasticity, if there is such an effect, from the effects of adding a paired couple term, which basically flips a pair of spins at a time, we also, as a check, look at this additional term with a negative sign. And of course, the addition of this term in the red box to this Hamiltonian gives us still a stochastic Hamiltonian, but now it's a stochastic coupled Hamiltonian. So we have basically three coupled Hamiltonians, two non-stochastic, one stochastic, and then we compare all of them against the case where we only have the transverse field as our driver Hamiltonian. OK. So before showing you the results, just a quick note on what our tools are. So we basically do exact diagonalization to look at to calculate the energy spectrum and find the result, the solution to our problem Hamiltonian, and we also carry out and also read off the size of the minimum gap, and then we also carry out unitary Schrodinger dynamics to try to simulate the process of annealing, and so. As our metric, we basically use success probability, which in this case is defined as the overlap between the true ground state of the system and the ground state that we read off from the Schrodinger simulation squared. OK. With this method, we can also calculate residual energy. But again, I'm not going to show you the results for residual energy. I'm just going to focus on success probability as our metric. All right. So let me start with the data. So this is a result of this. So in this plot, I'm just showing you the distribution of probability for a system of 15 spins, 10,000 instances. And you can see that there's a huge peak around 1, which basically indicates that the majority of problems that we're looking at are pretty easy, just with an transverse field driver Hamiltonian. So we do one level of post-processing. So we just get rid of the instances which already give us a 99% probability. And we end up with this shape, which is still the majority of cases are pretty easy, but it's at least a bit more evenly distributed. So in this case, if we sort of get rid of the easy problems, we end up with about 58% of the instances, the original instances. All right. So to make a comparison, so this is sort of the last definition that I'm showing here. to actually try to quantify the gain that we get from each type of coupled fluctuation, we define the success probability enhancement, which is simply the ratio of the new probability resulting from coupled Hamiltonians to the old probability resulting from just a transverse field term. And we define it to be greater than 1. And also we define success probability enhancement ratio, which is basically the number of those instances which will show improvement once we turn on the coupling terms divided by the total number of instances. And we define it as such that it's the number of those instances which provide better probability than X, and also better than every other coupled Hamiltonian that we're looking at I just define it to be greater than 1. I exclude that. I just define it this way. Yeah. All right. OK, so again, for the case of n equal to 15, these are the success probability enhancement ratios that I see for the 3 types of coupled Hamiltonians that I have. So for the stochastic case, it's about 66% of instances show improvement once I turn on the minus XX term. And then contrast that with the success probability enhancement ratio that I get for non-stochastic cases, which is significantly lower. It's 2% for the uniform case and about 11% for the mixed case. But now, if you look at the distribution of this enhancement, we see that for the stochastic case, this is basically peaked around 0. So in the bottom line, I'm actually showing you the log of P enhancement. So 4 basically means 10,000 times better. So here, the maximum is about 1,000 times better, and the 99th percentile value of P enhancement is only 10. So I'm showing you this data to basically indicate that this is a very peak distribution. And the majority of cases that we see enhancement, the enhancement is pretty marginal. Now this is the distribution that we get for the uniform non-stochastic case. And you can see that it's already a lot more evenly distributed. And you can see that the maximum and the 99th percentile value are both around 10 to the 4th. So things get better about 10,000 times better in this case. And for the non-stochastic case with the mixed sign case, again, we can see that this is somehow in between the first two. The maximum improvement that we can see in this case for this particular system size is huge. It's about 1 million times. And then the 99th percentile is about 10,000. OK. So just to sort of recap the data that I showed you in the previous slide, it seems that for the stochastic Hamiltonians, basically improve a large fraction of instances, but the actual improvement for the majority of cases is small. Whereas for the non-stochastic case, it's much smaller fraction of instances that show improvement, but the actual improvement can be large. So now let's look at the particular instances that are affected by each type of Hamiltonian and see if we see a pattern there. So here the blue bars correspond to the distribution of those instances that the probability of those instances that actually result from an uncoupled Hamiltonian, but for those instances that will show improvement once we turn on the minus XX terms. Oh, really? OK. OK. OK, and then the red line, basically, the red bars basically show what happens once we turn this on, and we see that it's actually it's mainly the easier problems that are being affected, and this is a scatter plot of the same thing, new probability versus old probability. You see the concentration of points is there. For the non-stochastic case, again, we see that it's the opposite behavior. Basically, the peaks are around p equal to 0. Which basically means it's the harder problems that are being affected by the non-stochastic Hamiltonians. And you can see that from these scatter plots better. The concentration of the dots are on the px equal to 0 on the vertical line. So then it seems that for the stochastic Hamiltonians, basically, they improve easier problems, whereas for non-stochastic ones, it's mainly the harder problems that are being affected. So what is going on? Basically, the only clue that we have with the tools, with our numerical tools, is just the data that we can get from the spectrum. And then the usual suspect is the size of the minimum gap. So what happens with the minimum gap? here, again, it's probably better if you look at the scatter plots. This is a plot of new gap versus old gap, and you see all the points are above the line, which basically indicates that for stochastic Hamiltonians, the size of the gap increases. In contrast, for non-stochastic ones, we can see that there's not really a real pattern. The size of the minimum gap can get smaller, can get bigger, can stay unchanged. So it seems that for stochastic Hamiltonians, they basically improve They basically improve the size of it. It's sort of likely scenario that they actually improve the size of the gap, and thereby they increase the probability. And so here's an example for a very small case, n equal to 6. And so this is a plot of the gap with a minimum gap, with one minimum gap. And then this is, so here the blue line is the overlap between the probability, between the ground state of the true ground state of the system and the wave function from the Schrodinger equation. And then the green line is basically the overlap between the Schrodinger wave function and the first excited state of the system. And you see that once we arrive at the minimum gap, they switch. So we end up with a bad probability. Now, if we turn on the non-stochastic terms, then we see that the gap actually sort of increases a little bit, and as a consequence, it really doesn't really affect the probabilities that much anymore, and then the probability is basically increased. So it seems so what happens in the stochastic case is kind of makes sense. Now, what happens in the non-stochastic case? In the non-stochastic case, we see that for the majority of cases, we basically don't see a pattern between the change in the size of the gap and what happens with the probability. So what is going on here? So here I'm actually going to give you a very hand-wavy explanation. And so sort of this is basically sort of more of an intuition than actually any real proof. So just take it with a grain of sand, solve. So in this Hamiltonian that we were studying, so when I have plus XX terms, so these XX terms are defined on a fully connected graph. So they basically, just having these antiferromagnetic couplings, they basically leads to frustration in the x direction. And now when having this frustration in the x direction, basically, this additional frustration basically means we have leads to having near degenerate states throughout our revolution. And then the presence of these near degenerate states basically means there will be additional Lev anti-crossings along the path. And I suspect that these additional anti-crossings actually can help. And this is one example again. So here I have a minimum gap that is very small, and then this is what is happening to the two probabilities for the ground state and the excited state when I don't have any coupled terms. And now once I turn on the coupled terms, I end up with two level crossings. Both of them are fairly small. And then this is what is happening to the probability. It basically comes down, and it has a chance to come back again. And for the cases that I have looked at, this seems to be, especially when the change in probability is large, this seems to be the dominant effect, at least based on the data that I had so far. And then this is a plot of the number of level crossings. Again, the horizontal line corresponds to the x only, and the vertical line corresponds to xx. And you can see that for the uniform non-stochastic case, the number of level crossing increases, and it can increase a lot. Similarly, for the case of the mixed sign case, whereas for the stochastic case, for the majority of cases, it seems that the number of level crossing actually decreases. So basically, this sort of leads us to thinking that, for the non-stochastic, whereas the stochastic Hamiltonians seem to improve the probability by increasing the size of the gap, maybe one mechanism behind the fact that non-stochastic Hamiltonians seem to improve the probability is that they actually increase the number of level crossings, and thereby provide the opportunity for the system to go back to the ground state if it happened to jump earlier on. And so far I showed you the results for just finite size systems for 15 15 spins. But this is sort of a plot of how things change as the system size changes. So this is a plot of success probability enhancement ratio as a function of system size. So the top line, the red line, is the stochastic case. You see that it sort of keeps increasing as the system size grows. And then the green and purple correspond to the two non-stochastic ones. And you can see that they seem to be kind of saturating at some point, and then they stay constant, at least up to the system size that we've looked at. And then this is a plot of the 99th percentile of the success probability enhancement, actual enhancement that we see. And you can see that for the stochastic case, I'm sorry that these numbers are a little small. For the stochastic case, the improvement is always less than 100 times. So it's fairly small, whereas for the non-stochastic one, it's a lot higher. You can see that the green and purple are above 10 to the 4th times better. So this is basically the phenomenon, and sort of to try to get a clue of what is going on, this is a plot of the size of the minimum gap, the median value of the size of the minimum gap for affected instances for each type of Hamiltonian. And you can see that contrary to what we expect for the stochastic case, the gap actually seems to increase as the system size grows, whereas for the non-stochastic ones, it seems to, well, fluctuate or slowly decreases. And this is a plot of the, so basically this plot indicates that for the stochastic case, again, it's the gap that is helping. And whereas in this plot, I'm showing you the ratio of the number of level crossings after I turn on the couple terms divided by when I don't have couple terms. So this line here, so the red line is actually below 1, which basically means for the majority of cases, the number of level crossing decreases when I turn on the stochastic terms, whereas for the non-stochastic ones, it actually almost always increases. So with that, this brings me to my summary. So I basically showed you that for stochastic coupled Hamiltonians, they improve large fractions of instances, and then these fractions actually increase with the system size. The actual improvement is small, and then they tend to improve on easier problems with larger gaps, and they seem to improve the probability by increasing the size of the gap. And in contrast, for non-stochastic Hamiltonians, they seem to improve smaller fractions of instances, and these fractions remain more or less constant as the system size grows. The actual improvement can be huge in some cases. They mainly improve on harder problems with smaller gaps. And one possibility of just thinking how they actually do this improvement is just that the additional frustration adds to the number of level crossings, and therefore there might be sort of more chances for the system to just relaxes back to its ground state. So with that, thank you very much for your attention.
Questions, of course.
Okay, I'm impressed by your very impressive set of data. And I have a couple of comments according to my experience with the mean field model. Please. One is that the non-stochastic term should be stronger than you used in your simulations S times 1 minus S to really extract the power of the non-stochastic effects.
Okay.
So you multiply the term by the factor of 10 or something like that. Then there is a possibility that dramatically different behavior may emerge, according to my experience. And another comment is that you use just quadratic term, squared term of as the representative case of the non-stochastic term. One of the reasons was that it introduced degeneracy, frustration. But according to my experience with the mean field analysis, even the cubic term works.
Say it again, sorry?
Cubic, three body interacting non-stochastic term.
Okay.
So I'd like you to try.
Okay, yeah, sure. I mean, I sort of wanted to start with the easiest case, but yeah.
So I totally agree with your
interpretation of frustration. And actually, I was talking to Nishimori-san a few months ago about exactly the same interpretation. But what could happen is because in the x direction, you're creating frustration, you're actually creating parallel paths. And instead of having one adiabatic path, you're having many adiabatic paths going together. So I'm wondering whether this effect can be simulated by just randomizing path in a stochastic problem and get the same randomization of the gap and enhancement of some problems versus other problems at the Eddie Farhi have experience.
Okay, well, I mean, I have no comment at the moment. I have to think about it. Yeah.
Well, let Eddie have the last word.
Well, I mean, I did a study on something similar, and what we found is in a way consistent with what you find, and I do see an algorithmic possibility here, which is that if you have an instance, you run it non-stochastically many times with different paths. The real question is, if you run it 100 times, do you get one big improvement? Because that's all you need to solve the instance. So it's, so for example, when you say the actual improvement can be huge and mainly improves on harder problems with smaller gaps, I mean, we found that, but we also found that if you do it enough, you always hit a winner. In other words, you find a path that improves the gap a lot. So that's very encouraging from an algorithmic point of view.
Okay.
And that's consistent with what you're saying.
Okay.
Okay, let's thank Layla.